Hello, Science 30 students. We're going to do a quick problem or two here from page 381, question 36, and then it'll be followed up by a second video with question 37. Now, these questions are textbook questions, but they were assigned in one of the study guides. I don't even have the study guide in front of me, so I'm not sure the number. I'll add that into the title of this so you'll know which one it is. Some of these questions are appropriate for Science 30. They are curricular and some of them aren't, but I'll go through that as we get there. So the first one is perfectly acceptable as a series of questions which could show up for a final exam. So it's a series circuit, and in a series circuit we have a few things happening. They separated the cells of the battery, so they put a 2-cell battery, but they separated them. First one is a 6-volt, and the second one is a 6-volt. Now these two cells are in series, which is really important. So that's going to bring apart something. The voltage supplied, because it's in series, uses Kirchhoff's law for voltage for a series circuit, which is that the total voltage is the first plus the second. And that's something you'll be expected to recognize in a series circuit. So we'll get that to that. We'll write that in a second. So the electrons are going to leave, gang up, have a total of 6 volts potential difference available, and then they get to the first bulb right here. And now they call that R2, but again, electrons go from negative to positive, so they're going to go this way around the circuit. It's a direct current, so it goes in one direction only. When they get to this first bulb, here's the thing about electricity. It's going to dump some energy for this particular resistor, but it's going to save enough for this one as well. So these voltmeters at the top are actually measuring the potential difference used, or potential dropped. That's the way we usually refer to it. The ammeter here, ammeter 2, and ammeter 1, all of the current has to flow through it, so the current was stay the same all the way through. So we're going to find that in a second, but A1 will equal A2. The voltage drop on 2 will be different than the voltage drop on 1 because it's a bigger resistor. Okay, so that just gives you a bit of background as we start to work through answering these. The reason I'm giving this video, putting it in kind of first, I have had questions about this already, so we'll follow up on it for everybody. So when we get to question A, determine the total voltage available for the series. So it's going to come from the two different sources, V1, the first cell, and V2, the second cell. Because they're in series, there's only one pathway for the electrons to flow. The formula Vt equals V1 plus V2 takes into account. That's not true in a parallel. Most of the time when you see that, most of the devices you put your batteries in, they have to go in series that way. There are a few examples that when we get back to class I can make a reference to, if we get a chance to, or later on when we talk about this a little more. So total voltage of the first cell, 6.0 volts, and the second is the same, to give us a total potential difference supplied of 12 volts. So that's how much potential difference is available. Now remember that potential difference, voltage is the amount of energy, two different places per coulomb of charge. Now when it comes to resistance, again, this is Kirchhoff's laws. For resistance, this is curricular and this is something you do have to know, is the total resistance for a series circuit. Only for a series circuit is the resistance of 1 plus the resistance of 2. So in this case, we'll use their numbering, even though they're coming in the reverse order. 20 ohms plus 40 ohms is going to give us a total of resistance in this circuit of 60 ohms of resistance. Now for C, where it's going to ask us to calculate the total current, or the current flowing through these ammeters, again, as the current goes through, it's going to continue all the way through the entire circuit. The current doesn't change in this because it is a series circuit. There's only one pathway, so it keeps all of the total current together going through. In a parallel, the current will split. And we'll see that when we get to question number 37. So if that's the case, we're going to use our total resistance and our total potential difference to find our total current. So to solve this, we're going to use Ohm's law. V is equal to IR But in this case, we're looking for I. So I is going to equal our potential difference divided by our total resistance. So put in our substitution, our total voltage potential difference is 12 volts. And our total resistance calculated in B to be 60 ohms. Now 12 divided by 6 would be 2, but it's divided by 60, so it's going to be 0.200 amps, or 0.2 amps. So question D wants us to find what the voltmeter readings for resistor 1 for resistor 2 is going to be. So again, there's going to be a different potential difference dropped at each of those two different bulbs in this case. So we have to treat each separately. So again, we're going to use Ohm's law. We're going to go V equals IR. The current is constant all the way through this circuit at 0.2 amps. The resistance for R1 was 20 ohms. So 0.2 times 20 is going to come up to 4.00 volts. So that first one will read 4.00 volts. So for the second resistor, we'll use the same Ohm's law technique. 0.2 amps times 40 ohms. 0.2 times 40 is going to come up to 8.00 volts. Now there is a second way we could have done that, because we do know Kirchhoff's law for voltage tells us in series, VT is. Sorry folks, my microphone clicked out there for a few minutes. Let's see if we can get through this question and take a pause and charge it a bit. So as I started to say, Kirchhoff's law for a series circuit says that the total voltage is equal to V1 plus V2. So we knew that total voltage was 12. We found that from the source. If there's, again, potential difference voltage is like eating at grandma's house. Whatever she puts on your plate, you eat all of it. Whatever potential difference is supplied by the batteries will be used by the resistors in that circuit. So when we found V1 was 4.0, well, we know that V2 then had to be 8 in order to add up to 12. So we could have done that using our voltage as well for Kirchhoff's laws. When it comes to series circuit, if one bulb turns out, they all burn out. Because each bulb is part of the circuit. If one burns out, I shouldn't say burns out, goes out. So those are like old-fashioned Christmas lights that you have to be pretty old to remember those type, but the good old is that was what we had. All right, so that's question 37. So moving on to question number 37. So on question 37, it's quite a bit different. We're dealing with a series or a parallel circuit. So first of all, we've got our two cells, each 6 volts, but they're now connected in parallel. This is actually not curricular. The way it works, they have to be equal-sized sources. Kirchhoff's laws for potential difference is V total is equal to V1, which equals V2. So in other words, the total voltage is only 6.0 volts supplied. It's not going to be the same as a series circuit. So in parallel, you only get 6 volts even though you have two 6-volt cells out of this. So why set them up this way? Because some devices do. Our wireless keyboards are set up that way. Some old digital, very old digital cameras were set up that way. On the old yellow rescue truck, once upon a time, we had two 12-volt batteries were set up in series, or sorry, in parallel rather than series. So you still just got 12 volts. However, the advantage is you'll get more current produced, so you can do a bigger load. And that's the purpose of doing it that way. However, for Science 30, that is not curricular. So you don't actually have to know that one. So you can put a little star beside that. You will never be situated with that. Okay, for question B, 37B, Now we've got the total resistance when they're presented in parallel. So you've got two different resistors, and now they're in parallel. This is, I repeat, this is something that you're expected to utilize in terms of your curricular expectations. So the formula for Kirchhoff's laws for resistance in parallel is 1 over RT equals 1 over R1 plus 1 over R2. That's clearly labeled on your formula sheet, on your data booklet, and it tells you that that is for parallel circuits. So you're going to expect it to know how to use this formula. You're also expected to be able to look at this particular circuit, or look at a particular circuit and know that it is indeed going to be a parallel circuit, identify what's necessary. So I still expect you to then substitute in 1 over 20 ohms for R1 plus 1 over 40 ohms for R2. But I don't want you to do this as a good math student would in terms of doing fractions. Remember, we're not looking for 1 over RT. We're looking for RT. So I'm going to show you on the calculator the keystrokes that I would like you to do for this particular question. So if you pull up your calculator, and it's going to have this inverse key right here. So remember, an inverse key, put in the number 2, hit the inverse key, it's 1 over 2, which is 0.5, which is 1/2. All right, so what I want you to do is just simply this. Take R1, which was 20, and then hit your inverse key. That means 1 over 20. You're going to add that to the second resistor, R2, put in the number 40, and hit your inverse key. There's a big advantage as to doing this procedure. Trust me, it'll cut down your mistakes, so please do it this way. When you hit enter, that does not give you RT. What you've calculated there is 1 over RT. So that number is 1 over RT. We don't want a 1 over RT. So rather than, again, mess with your mathematics and your fractions, just hit your inverse key one more time. So again, hit your inverse key for that answer, and it gives you 13.3. So that's your total resistance. Now that just may seem a little counterintuitive to you. You had two resistors, one at 20 and one at 40. When they're put together in the same circuit, suddenly what happens is the total resistance, this is the total resistance for the circuit. I should have written it like this, that RT is equal to 13.3 ohms. The resistance is less than either one of the two resistors, but that's the way parallel circuits work. That's the reason that the load is often put into that. So it's very counterintuitive to see it go down like that, but that's just the way that Kirchhoff's laws for resistance work. Okay, moving on to question C. Now we want to calculate the total current. So the total current is what you're going to find going through this ammeter. Because what happens when the current comes down, current's going to come down from here. It's going to join with the current from here. That's going to be the same current as our total current. But when it gets to this point, again, it's like it's psychic. It says, you know what? I'm going to split up because I need to send some current this way, but I need to send some up this way. So the amount of current it sends here is different than here. Now, if they were both 220 ohm bulbs, then it would equalize it and send it. The way the current works, though, it's smart. It says, I'm going to send more current where there's least resistance. So since this is half the resistance, it'll get twice the current that R2 will. But when they come back up, they join up again, and they're back to the IT. So this is current would be I1. This is going to be I2. But in this question, we're looking for the total current, so we have to use our total potential difference or total resistance. So the total voltage in this was just 6.0 volts by Kirchhoff's laws. The total resistance we calculate to be 13.3 ohms. Let's go ahead and solve that for you on the calculator. I've got 6.0 divided by, and I want to divide it by that 13.33, so I'm just going to put in, that was my last answer, and I get 0.45. Let me make that a little bit clearer for us. So because I've done these for a long time, I know that that's what they'll join back up. So when they split here, we said twice as much goes this way, sorry. So I know right away, just by looking at it, if I take that and divide by 3, I get 0.15. I double it for here, so it'll be 0.3 is going to go through here. And for this one, it's going to be 0.15. Twice as much through where there's half the resistance. But we'll calculate those out separately in just a bit. Okay, so to calculate those using Ohm's law, V equals IR, we manipulate that so that I is equal to V over R. So just for those two separate lines, so first of all for R1 and then for R2, what's happening with the current here? Now we already said we know that that's going to be 0.3, but let's just go ahead and prove that. The way it works is, again, the total voltage, we calculate it to be 6.0 because it's supplied in parallel. The way it works for each branch of the circuit, each one gets equal potential difference. Each one gets 6 volts. So when I look at I for ammeter number 1, it's going to be the 6.0 volts that each branch will get. And the resistance is 20. When I go 6.0 divided by 20, I get 0.3. And that's what we predicted. Do it for the second resistor. Same formula. Still 6.0 volts. Everybody gets 6.0 volts. This one has 40 ohms of resistance. So I'll go ahead and put that in my calculator just for those of you who want to ensure I'm not doing any voodoo magic here. 6 divided by 40, 0.15. So in terms of ammeter 3, that's going to be the total, which we already calculated using Ohm's law, to be 0.45 amps. However, Kirchhoff's law for a parallel circuit, we could do it this way as well. And see that that's to be true. And that's how I did that prediction in the first place, that I knew what they were going to be ahead of time using Kirchhoff's laws. So Ohm's law, Kirchhoff's law. Explain why. Well, first of all, why would this be true? Because first of all, first reason is that's what Kirchhoff's law or Kirchhoff's law IT equals I1 plus I2. How did he determine that law? Again, it was empirical. He worked on a whole bunch of circuits and he found that to be true. So this again is a parallel light, parallel circuit for these lights. What's going to happen if one of the bulbs burns out? What happens to the other one? Absolutely nothing. It continues the same brightness. It just uses what it has, and I guess the only thing is those batteries make it last longer. That's about the only thing. So nothing else happens in a parallel circuit. One of the advantages of, certainly for Christmas lights, being in parallel. That's it, folks. Hopefully that helps you get through this question.